Temme. So it's my pleasure to introduce our first speaker for the afternoon, Kristan from IBM, who's going to talk about approximate algorithms for quantum many-body problems. Thank you, Kristan.
Hi, James. Thank you very much, and thanks everyone for joining. I'd like to thank the organizers for inviting me, and especially for setting up such a nice conference in such a short notice, all virtually. So what I'll be talking about is joint work with Sergey Bravi, David Gossett, and Robert Koenig. And I'll be talking about approximation algorithms for quantum many-body problems. So maybe as a heads up, so this is about classical approximation algorithms to quantum many-body problems, right? So that said, so we all know that solving quantum many-body problems is actually very challenging classically, which is particularly the reason why we would want to have a quantum computer in that domain. And there's various reasons that you're probably all familiar with of why this is so difficult. But there are certain settings, and there's been a trick that has been sort of in the toolbox of various people working in that area, which are variational algorithms. And so the task here is, of course, as everyone knows, it does allow you a way to basically tame that exponential scaling by considering particular classes of wave function or ansatz states that only depend on a polynomial number of parameters if n particles are present. Okay, and so some examples for those variational trial states people are very familiar with are sort of mean field states, matrix product states, projected and entangled pair states, Meras, neural network states, and so on, all for quantum spin systems. And for if you look at fermionic many-body systems, probably the most famous ones are Hartree-Fock theories and Hartree-Fock-Bogoliubov theories, where one has particle number preservation while the other doesn't. So to be clear, right now, what I'll be talking about are actually the more mundane trial states. In that setting, I'll talk about mean field states, product states for quantum spin systems, and talk about Hartree-Fock states, or so Slater determinants, and later, which will not turn out not to be very enough for what we want to do, Hartree-Fock-Bogoliubov states, which are Gaussian states that don't have particle number preservation. Okay, just to give you the in of that, what the main question is here is, so we care about, are you able to give a formal guarantee on energy estimates that you obtain using such methods? So what we care about is basically, okay, you know in principle, if you get to vary over all allowed states in Hilbert space by Ritz variation, you're always going to end up with a max with your extreme eigenvalue. In our case, in the setting of approximation algorithms, it becomes a lot more convenient to be talking about the maximum eigenvalue as opposed to the minimum eigenvalue. And it's sort of like the standard notation there and approach to doing this. So we'll stick to that. If you don't like that, you can just flip the sign of the Hamiltonian essentially and treat the smallest one as the largest one as you please. So if you vary over all quantum states, you're guaranteed to actually obtain the largest eigenvalue. However, so if you start to restrict and only look at a subclass of variational states, everyone knows that that you're only going to obtain lower bounds for the maximal eigenvalue, or upper bounds if you want to minimize them, right? So you have now a restricted class of states. They naturally are going to give you a lower bound to the actual state. And now, if you want to have some guarantees, which I'll talk about a bit, there's some caveats. So there's now two questions that you might ask, right? So if you're given a set of variational trial states, then there's the first question is, so out of this large arbitrary set of variational trial states, what is actually the best possible trial state? So how well does your set of variational trial states do in approximating all quantums, in approximating the energy of that Hamiltonian? And the next question is, are you actually able to efficiently compute that particular trial state, or which class of trial state are you able to compute efficiently? Because even though you may now only be looking at a reduced set of states, and you've simplified the problem from the point of view that that you're not looking at an arbitrary Hilbert space anymore, there's still a challenging computational problem. So there's these two things, right? And so the lens we'd like to take to look at this are so-called approximation algorithms. And just to give you sort of an easy overview, what they do. So suppose you're given an NP-hard, or like generally a hard optimization problem that's sort of given in the standard form. You say, oh, you want to maximize some cost functions subject to some constraints. And what you want to do in these approximation algorithms is you want to guarantee that there's an efficient algorithm, so one that you can, that scales polynomially in the number of parameters, that does find an approximate solution to your best optimal solution, which has a provable and guaranteed window or guarantee for the value of the cost function, right? So you know that, for instance, in our case, initially, if you look at the maximization, there's always a lower bound. But what you would want to worry about is basically, you want to have a window, upper bound, lower bound for the very same state, and want to see how well that does, okay, that you're given. Right, one of the most famous approximation algorithm examples that there is the Goemans-Williamson algorithm, which is sort of like, you can think of this as an Ising model, and you want to, on an arbitrary graph, and what you want to do is you want to start cutting all those links in such a way that you cut the most number of links, basically. That's sort of the max cut problem. And there's an approximation algorithm for that, which is the Goemans-Williams algorithm, that gives you the following guarantee. So it gives you a constant fraction of the actual energy value for that problem. And the way that has been achieved is basically through semi-definite programming like relaxation method, which can be related to various hierarchies and so forth, but this is sort of like the first step there. And that's sort of a polynomially efficient algorithm that gives you plus some randomized rounding. And so what we want to do is have the same thing now for quantum Hamiltonians, essentially. And this is now sort of a two-step process. So the first step is find a good or easily tractable class of trial states that, and for which you can guarantee that they do reasonably well. And the second thing is show that you're actually within that class able to guarantee such a window that works, okay? So what I'll talk about first are mean field theories and states and spin systems. And what we're going to consider here is the problem of looking at two local Hamiltonians. So you consider two Hamiltonians, they're defined on qubits, have pairwise interactions and single qubit interactions, if you like. And right now we're not placing any constraints on what the couplings between those pairs are. They can all couple to everything and so forth, and they can vary arbitrarily. So in principle, you already know that, okay, you can encode some hard problems into that. And we asked for a specific constraint that there's no identity term in that, and you asked that H is traceless. Okay, and so our initial motivation for looking at that came actually from a paper by Lieb, which is called the classical limit of quantum spin systems. And when looking at that paper, Lieb had a way of giving a guarantee of how well product states ultimately do in approximating ground states of Hamiltonians. Okay, so what we're going to consider is now the difference between the approximation ratio between the largest eigenvalue as compared to the best attainable attainable value that you would get from taking a product state approximation. So obviously, as we said before, since this is a variational principle, the product state is going to do always lower than the actual largest eigenvalue. But now the question is, how small can that ratio be? Can that be really bad or not? And so what Lieb showed is basically in that paper that I just mentioned is, there's always a constant fraction approximation between the optimal product state and the actual true largest eigenvalue for any traceless two local Hamiltonian. And the way that Lieb proved that is basically he went to look at certain bounds for partition functions and had like an upper bound for the partition function that was a classical partition function. You can take the zero temperature limit of the classical partition function and that way sandwich this. It's actually a pretty technical proof. But if you know a little bit of quantum information, then the proof can actually substantially be made easier for that setting and actually reduces to just a one-liner. And the trick is basically you look at noisy channels, depolarizing channels. So you can look at a single qubit depolarizing channel. And let's do that for the case where H is equals to 0, where one we have to point out, because in principle, the general case where you have a single qubit terms as well, can be reduced to that. So it's still the same. So it's fine to say that set H equals to 0 by some reduction. I won't mention that and how that works. But okay, so you know that if you look at the single qubit depolarizing channel, that this channel is actually entanglement breaking for a depolarizing rate, which is basically less than 1/3. So if you have 1/3 depolarizing noise, then what you're guaranteed that no matter what input state you use, you're left with a unentangled mixture of quantum states for an arbitrary input state. And so this is also the case if you do that for n for all of the n for an n qubit state. If you start depolarizing all the n individual qubits, the full state after having passed through the single qubit depolarizing channel is going to be an unentangled mixed state that you have in the end, right? Okay, so knowing that, you know that if you were to now use your favorite, for any input state rho, you apply d to the rho to the n, you know that actually d to the, like applying the depolarizing noise to that full state generates a classical mixture. So you know that if you were to maximize over this, this is clearly lower bound to the best possible product state because you're maximizing over a restricted set of product states here. And so knowing that, so okay, you have that lower bound. The next step is you observe that D is actually a self-adjoint operator under a Hilbert-Schmidt inner product. You flip it over to the Hamiltonian and have D act on the Hamiltonian. And now, since the Hamiltonian is a two-local term, and you know that for depolarizing noise, Paulis are essentially eigenvectors of the depolarizing noise map. You just basically pick up an epsilon square term for all the way two Pauli operators, and you know that the maximum on the right side is, if you carry that out, you basically realize that the maximum on the right side is actually lambda max. So what you have is you have a lower bound to the product state with a factor epsilon squared times lambda max, when epsilon squared is chosen to 1/3, which gives you exactly that, the very same lower bound that Lieb had in the paper in 73. Now here's the question: is that bound actually optimal? And is there something that does better? So what is the actual worst case approximation ratio? And so we did some numerical searches for the small qubit system going from 2 to 6 qubits and optimized for all the worst case instances. And the open conjecture is essentially that that this is that this number should be 1/3, based from numerical evidence. Okay, there's actually we're able to give in that paper. We're actually able to give a stronger bound if you don't look at the largest eigenvalue, but if you look at the quantity that is the largest absolute value of the energy, then we're actually able to prove a 1/6, but it's still not there as at 1/3. Okay. Now that we actually know that, okay, you know that for a product state you have a constant approximation ratio in energy. The next question is that we hadn't listed. So what is actually the best efficiently computable product state if someone gives you a problem? And people have done some quite some previous work on this. For instance, I would say like the closest one to this is work that was done by Aram Harrow and Ashley Montanaro in 2015, where they consider Hamiltonians and sparse graphs, and they obtain a bound for an efficient algorithm that is actually constant, but with but the assumption is that there's a sparsity in the graph and there's a fixed maximal degree in that graph. So which is something that we don't have. So there's other results by Brandau and Harrow from 2015, which gives sort of like an additive bound, and under different conditions, Garibian and Kempe were able to prove in 2011 the constant fraction based bound. So, but these are all settings which are not exactly the same setting, so it's not easy, so you're not able to directly compare the results that we have with that. Okay, so what we have is a result in this setting where there exists a efficient classical algorithm that is going to provide you with a product state that is going to be able, you're guaranteed to have an approximation of lambda max divided by order of log n number of qubits. And you're going to be able to produce that state with high probability. And now you could wonder, is this log n actually optimal, or could you do better? And there's results by Aurora et al. From 2005, which basically relates to looking at an Ising model. In that case, that says, well, if it would be quasi NP hard to basically do better than that bound. So you could probably assume that this is not the case. Okay. So how does that algorithm work? We're looking at the same trick as an SDP relaxation by as it was done by Gaussian and Williamson. And the trick here is basically you basically, for a given n-qubit state, you can define the covariance matrix for two Pauli operators, and there's some simple constraints that this genuine two particle reduced density matrix actually satisfies. So you know it's positive semi-definite by construction, and trivially the diagonals are all one. These are all things that such a matrix satisfies, but this is of course not exhaustive, because otherwise you'd be able to characterize those two particle correlation functions, which is a very difficult problem known as n representability. So this is a set of relaxed constraints for that. Okay, and so, but just having access to that covariance matrix would allow you to actually compute energies, and being able to optimize over all possible covariance matrix would actually allow you to solve that problem. And the only thing you have to do, since it's all two particles, actually, that you can write the expectation value of energy in terms of a trace inner product between the coefficient matrix of the Hamiltonian and the covariance matrix. Okay, so you're in a very similar setting as Gaussian-Williamson earlier. So as we said, what we're going to look at is an SDP relaxation of that problem. You know, the original problem that would be exact is, so you get to maximize over all genuine two-party covariance matrices of some n-qubit quantum state, and then you would, the maximum over that optimization problem is obviously the quantity you want. So what we do now is basically we relax that constraint with an easier constraint, as we pointed out before. And what you have now is that because it's a relaxation, you immediately have a larger class of a larger optimization problem. So your optimal value of that relaxed problem is an upper bound to the true value, right? And so then the question is, okay, after you've done that, how do you get back to the product state? And moreover, how are you able to actually show now that you have from that approach to obtain that window? And so what we use here is a randomized rounding scheme, which is from Cherika and Wirth. It's an adaptation to that to our setting. And so in order to do that, you say, if you go and solve that optimization problem, which is an SDP, which is sufficiently solvable, you can essentially do a similar trick as in Gaussian-Williamson initially. You basically factorize that matrix as a ground matrix. You could use sort of whatever decomposition you like. You can do typically like Cholesky if you like that. And once you have that decomposition, you draw a random vector in R to the 3n. So for 3n Paulis, R to the 3n, and where the entries are Gaussian normal distributed around 0. Okay, and then once you've done that, you basically start projecting all the factors in the covariance matrix down to that randomized vector. And you have to renormalize that, and you have to choose a normalization factor called a t that ensures that with high probability, you're actually going to end up with a vector that sits within the Bloch sphere of every individual qubit. Okay, and so what you do then is basically you have this randomized rounding procedure gives you, with high probability, gives you a set of components of each individual qubit Bloch vector. And now we have to think about, well, how large do you have to choose that? And actually, the paper is a bit different, but the way you go about this is basically, okay, let's look at the expectation value that you obtain from this rounding procedure, right? And so you know that if you introduce this and compute the average of this rounding procedure, you compute the, which is this expectation value, you realize that, okay, if you introduce the factor of 1 over t squared, you have this thing. And due to the rounding, this is actually a resolution of the identity, which means that you're actually going to end up, the expectation value you're going to end up is defined as t squared times the optimal value of your SDP that you obtained, which is this lambda SDP value. Okay, and you know that by the lower bound that we have, because it's this relaxation, that lambda max is now a lower bound to this quantity, so you're actually going to have an upper bound to lambda max divided by t squared. And now what you have to worry about is, well, how large do you choose that t? Well, you want to end up with a t so that with high probability you're going to end up with an element of the Bloch sphere, And to do that, you have to choose something that scales as square root of log n, which in the end then essentially introduces the fact that your expectation value when you do the sampling basically is guaranteed with high probability to give you a product state that is larger than lambda max over log n squared. And naturally, because it's a product state, it's of course upper bound by lambda max. Okay, so we've done that for product states. So what is the next thing you can try? Well, the next thing you could try is basically go out and use that machinery or comparable issue machinery to fermionic system. And the first round, what we'd like to do is we'd like to consider fermions and the Slater determinants. So to define fermions, we're going to work in the second quantized picture, where you basically have creation and annihilation operators that put fermions in particular modes, and we generate the Fock space this way. And what we're going to look at for is an interacting fermionic system. And so you have the system, and the system is set up in such a way that the Hamiltonian is given by a free contribution, which is sort of like a free fermions moving, and you have the actual two-particle interaction part. And you can introduce a constant with energy shift that allows you to basically make this thing traceless. Okay, and so if you were to try that with Slater determinants as a Hartree-Fock as a trial state, you could wonder, okay, let's go and define what the best value is for the Slater determinant. And what you'll find is basically the first thing you want to ask is, okay, is there a Leibniz type theorem for, we had product states, is there a Leibniz type theorem for Slater determinant so that you can bound a constant? But unfortunately, there's a counterexample that you can find. And so the counterexample is actually a model called Richardson model, which is an interacting Hamiltonian, which basically models in some sense pairwise hopping, an interactive two-particle interaction where you mediate pairwise hopping. And the cool thing about that model is that it's actually solvable. So you do know what the largest energy eigenvalue is. And if you work that out, you realize that, well, the largest energy eigenvalue is quadratically in n, whereas the Slater determinant is only going to give you at most an energy approximation which scales linearly in n. So the ratio vanishes at least 1 over n in the asymptotic limit. So it's not possible to actually show a constant fraction approximation bound for Slater determinants, right? Also not if you do the shifts, because this one is actually not shifted, but fine. Okay, so that conjecture is wrong. So what we need is a class of more powerful variational states. And as I mentioned before, the second class, we're going to look for our Gaussian states. And these are states that are not particle number preserving. And so they're best described in terms of Majorana modes. And they're essentially only fixed by the covariance matrix. And so given that you know the covariance matrix, there's a set of constraints that you can set, as you know that you have this anti-symmetry problem, you have a norm bound, and all these constraints satisfy a valid covariance matrix. And given the covariance matrix, and you know this being a Gaussian state, you know that all the higher order moments can be expressible through Wick's theorem by looking at products of that matrix. Okay, so in the end, what you do if you expand that, you realize that, okay, the energy actually for a Gaussian state is only just a quadratic function of a covariance matrix. So if you now look at the problem of optimizing this over all possible Gaussian states, you realize, okay, first of all, this can only do as bad as Slater determinants, possibly better, because Slater determinants happen to be a subclass of those. And what we're going to find is, if you look at this, you can prove by looking at lower bounds between Gaussian states and the largest eigenvalue that in this case, you actually end up with, for this example, you're going to end up with a constant approximation fraction in the asymptotic limit. So then the next question is, okay, for these states, can you prove an analog of Leibniz theorem? And the answer is, well, we don't know. That's still an open question, which I'm going to be mentioning in a bit. But what you can state is basically, in the end, that there's what we were able to state is that there is actually an efficient algorithm to approximate the best Gaussian state within O log n time. And by extension, unfortunately, because we're not able to go beyond that 1 over n bound, because we weren't able to prove the analog version of Leibniz theorem, we're going to end up with something that looks like an O(n) log n lower bound to find actually the best possible Gaussian approximation state. So as you can see, so the bound that based on that you only have at the moment is 1 over n log n, which is evidently not constant. So we don't believe that to be a tight bound. So the main tool to achieve this is basically a quadratic optimization problem with orthogonality constraints. So it's a polynomial optimization problem with norm constraints and so forth. And for that, there exists also an SDP relaxation with rounding that I'm not going to go into. It's similar in spirit, and that allows you to basically to find a relaxation of this problem by itself. And so what happens here is basically that now your optimization over only Gaussian states, as we had beforehand, is actually a special case of this. And so that relaxation works, right? And there's a different rounding procedure that you can apply to that. So that said, I think I'm pretty close on time. There's a bunch of open questions that I mentioned. Like the first open question is, in the case for product states, Leap was able to prove a fraction approximation fraction of 1/9. Based on the numerics, we're conjecturing that should be an approximation fraction of 1/3. Is there a way for you to prove that? So could you prove that? That's an open question. And the next question, which is probably very interesting, at least to us, is basically, are you actually able to prove an analog version of Leap's theorem in the fermionic setting, in the fermionic case, with a constant approximation ratio? To give you a suggestion, so the trick that we used initially was basically to use a fermionic channel applied to a general state that would end up giving you a mixture of product states. So in that sense, is there some analog or some other channel that you could look at in the fermionic setting where any arbitrary fermionic state is going to get mapped to a mixture of Gaussian states, fermionic Gaussian states, and so we don't have a concrete answer for that problem. So I think, yeah, with that, I'm towards the end of my time, I assume, and I'd like to thank you all, and I'm open for questions.
Thank you for that really interesting talk, Christian. So just as a reminder to the audience, please ask all your questions in the Slack channel. So we have a question to start us off from Duan Camps, which is, were fermionic Gaussian states not of a definite particle number? How can slated determinants be particular cases of Gaussian states then?
No. So Gaussian states are not of a fixed particle number. The slated determinants are the fixed particle number states. So if you look at arbitrary fermionic Gaussian states and restrict them to only live in one well-defined sector of the Fock space, then you end up with a slated determinant, right? So the class of Gaussian states is by that sense strictly larger. The only thing that is preserved is essentially particle number parity. It's parity of the particles. So the number of particles mod 2, right? So it's a strictly larger class. Yes.
So our next question comes from Kristan Temme. So can the Gaussian states possess a constant approximation ratio?
So they can. This is exactly the example that we looked at. So which I unfortunately ran through a bit. So in the case of this Richardson model, this is exactly what you're observing, right? So in the Richardson model, you basically have for slated determinants, you have an approximation that goes as 1 over n. Versus for the Richardson model, it's basically 1 minus 1 over n. So in the asymptotic limit, you're actually going to get a approximation of 1 for that particular model, right? So in that case, this is an example. So, but yeah, so there's no proof yet to whether this is generically the case. Yeah.
And so we'll have one final question now, which is from Ashley Montanari, which is, for qubits with d greater than 2, I guess we could use the same depolarizing channel argument. Does this give good bounds in this setting?
So d being what? Sorry, can you say
greater than 2?
Right. But d is the local dimension. Yeah. No. So we had something similar. Thank you, Ashley. So we had something similar. But the argument that we had was basically that in that case, you don't end up with a constant approximation ratio, right? So if I agree that say you say, okay, you could view this sort of as an n mode, if you want to like read the things as an n mode thing, and then hope that there's sort of like an n mode version of this. But then if you look at this and the necessity that you basically have that this turns into to the property that this averaging gives you end up with a fraction that actually goes as a 1 over n as well in that sense, which is like 1 over the local dimension, right? So in this case, yeah, is that the question you were asking? I'm not 100% sure of it.
Okay, so Ashley's now responding to the Slack channel, so I'll let you go to the Slack channel and we'll move on